Welcome to Study Loop.
So in this problem, we are given the reaction equation for the formation of ammonia from N2 and H2. We're given the value of Kp, we're given the volume of the reaction vessel, and we're given the equilibrium mass of ammonia. So in first part of this problem, we have to find out the equilibrium mass of nitrogen and hydrogen. So to do that, what we have to do first is we have to find out the equilibrium partial pressure of ammonia, and from that value and setting up an ice table and using the value of Kp, we'll have to find out the equilibrium partial pressure of nitrogen and hydrogen, and from the equilibrium partial pressure we can find out the equilibrium mass of nitrogen and hydrogen. So the first step here is to find out the equilibrium partial pressure of ammonia. So we are given the equilibrium mass of ammonia, and we know that there is a equation for the ideal gas, which is P equal to nRT. So we can utilize that equation to find out the equilibrium partial pressure of NH3. So PNH3 equal to nRT, where V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. So if we just rearrange this equation, we can write PNH3 is equal to nRT over volume. And now, so that again, the number of moles is basically the mass over molar mass. So the mass we are given, so the equilibrium mass is 1.05 gram. So we can write it mass over molar mass, that means 1.05 gram over the molar mass of ammonia, which is 17.03 gram per mole, times the volume is 1 liter. And then we have to write down the value of R, which is 0.0821 liter atm per mole Kelvin, times the temperature, which is given as 300 degrees C. In Kelvin scale, it will be 573 Kelvin. And if we solve this, we will get a value of 2.90 atm, atmospheric pressure. So this is the equilibrium partial pressure of ammonia. Now we'll set up an ice table, and from there we'll find out the equilibrium partial pressure of the reactants, which is N2 plus 3H2 will give us 2NH3. So the initial concentration of the nitrogen and hydrogen should be 0, and so we don't know the initial partial pressure. So what we're doing here is we are trying to find out the equilibrium partial pressure of nitrogen and hydrogen. So if we um, assume that we don't know the initial partial pressure of NH3, then but we know the equilibrium partial pressure of NH3, which we have just calculated as 2.90 atm. So we can write this value here, 2.90. And if we assume the change in the partial pressure of N2 and H2, and then we can write down for both of them, and if we assume the change is x, so for N2 the change will be plus x, and for hydrogen it will be plus 3x, and for ammonia the change will be minus 2x, but we don't need this for now because we know the equilibrium concentration of NH3. So the equilibrium concentration for N2 will be x, since it is 0 plus x equal to x, and for H2 it will be 3x. So now from these values we will have to find out the value of x, and from there we will be able to find out the equilibrium partial pressure of nitrogen and hydrogen. So now we'll plug in these values in the equilibrium constant expression. So equilibrium constant in terms of pressure for this reaction will be the equilibrium concentration of the product, which is PNH3, and since it has a coefficient of 2, we'll have to raise the power up to 2. And then in case of reactant, we have two reactant, which is N2. So in the denominator we will have the partial pressure of N2 times the partial pressure of hydrogen, and hydrogen has a coefficient of 3, so the power will be raised up to 3. Now the partial pressure of nitrogen, the partial pressure of ammonia is 2.90, so we'll write down 2.90 square over x for nitrogen partial pressure, and then 3x for hydrogen partial pressure, and whole cube. So if we solve this, and we're given the value of Kp as 4.34 times 10 to the minus 3, so it will be 4.34 times 10 to the power minus 3 equal to 8.41 over 27 x to the power 4. And if we just rearrange this, the equation will be 4.34 times 10 to the power minus 3 times 27 x 4 equal to 8.41. And solving this equation, we can have the value of x as 2.91. So now we know the value of x, and from the ice table, the equilibrium concentration, we can find out the equilibrium partial pressure of nitrogen and hydrogen. So equilibrium partial pressure of nitrogen in x, that means it is 2.91 atm, and then equilibrium partial pressure of hydrogen will be 3x, that means 3 times 2.91, which will give us 8.73 atm. So these are the equilibrium partial pressure of N2 and H2, and from the equilibrium partial pressure we can find out their equilibrium mass. So equilibrium mass of nitrogen will be, so what we'll do is we will rearrange the equation P be equal to nRT. So what we will do is Pn2 V is equal to nRT, and from here we can, so the mass is here inside this number of moles, so now we can just rewrite this N equal to Pn2V over RT, and since number of moles is equal to mass over molar mass, so we can write from here, we can write the mass equilibrium of N2 equal to Pn2V over the number of moles of N2, so the molar mass of N2, molar mass of N2 times RT. So what we've done is, so the number of moles equal to mass over molar mass. Okay, so the molar mass will go in the numerator, not in the denominator. So it will be P into V times the molar mass of nitrogen. Now if we just plug in the values, so P we have calculated as 2.91 atm, times the volume is 1 liter, times the molar mass of nitrogen is 28.0 gram per mole. And in the denominator we have R and T, so the value of R is 0.0821 liter atm per mole Kelvin, times the temperature, uh, which is 573, Kelvin. So if we solve this, we will get the mass of nitrogen as 1.73 gram. So this is the equilibrium mass of nitrogen. In the same way, we can find the equilibrium mass of hydrogen, which will be same as before. So the formula will be here: partial pressure of hydrogen times volume times the molar mass of hydrogen over RT. So the partial pressure of hydrogen we have calculated as 8.73 atm, times the volume is 1 liter, times the molar mass of hydrogen gas is 2.016 gram per mole. Value of R is 0.0821 liter atm per mole Kelvin, and the value of T is 573 Kelvin. And from here we get the equilibrium mass of hydrogen as 0.374 Kelvin. So 0.374 gram. So this is the equilibrium mass of hydrogen. So we have calculated the equilibrium mass of nitrogen and hydrogen, which was asked for in question A, and in question B, we have to find out initial mass of ammonia. And to do that, we have to find out the initial partial pressure of NH3. So the initial partial pressure of NH3 will be equilibrium partial pressure of NH3 plus the change, which we have calculated as minus 2x. Okay, so the change will be plus 2x. No, the change is minus 2x. Okay, the change is minus 2x, but since that means the initial will be this plus 2x. So the initial partial pressure will be 2.90 atm plus 2x, and that means it will be 2.90 atm plus 2 times x, which is 2.91 atm. And this will give us a value of 8.72 atm. So this is the initial partial pressure of ammonia. And then in part C, okay, so we have to find out the initial mass of ammonia. So we have calculated the initial partial pressure of ammonia. And from here again, using the same formula as before, we can find out the initial mass of ammonia. So again, it will be initial partial pressure of ammonia times the volume times the molar mass of ammonia. It will be over R and T. So the initial partial pressure of ammonia we have calculated as 8.72 atm times the volume is 1 liter times the molar mass of ammonia is 17 gram, and the value of R is 0.0821 liter atm per mole Kelvin, times the value of T is 573 Kelvin. From here we can find the mass of ammonia, and if we solve this we get the mass as 3.16 gram. So this is the initial mass of ammonia. And then finally per se we have to find out the total pressure. The total pressure will be simply the total of the equilibrium partial pressure of all the reactant and products. So the P total will be partial pressure of nitrogen at the equilibrium plus partial pressure of hydrogen at the equilibrium plus partial pressure of NH3 at the equilibrium. And if we just plug the values, so for nitrogen it is 2.91 atm, for hydrogen it is 8.73 atm, and for ammonia it is 8.72 atm, and the total will be 20.36 atm. So this is the total pressure for the reaction.